Most sunstone sold in jewelry stores worldwide is a completely different mineral from Oregon Sunstone. And the difference comes down to copper nanoparticles forged inside ancient Miocene lava flows.
Yeah, it is genuinely one of the greatest geological bait and switches happening right in plain sight.
Right.
You can walk into almost, any commercial jeweler, point to a piece of sunstone, and the salesperson likely has absolutely no idea they're selling you a completely different geological phenomenon than the legendary stones from the American West.
And that basically brings us to our mission for today's deep dive. We are plunging headfirst into this whole world of Oregon Sunstone.
Which is quite the rabbit hole.
Oh, it really is.
Yeah.
When I first gathered the sources for this, like the volcanology papers, the optical physics breakdowns, the lapidary forums where gem cutters share their absolute horror stories.
Those are wild to read.
They really are. And the historical records, too. I figured, we'd be talking about a pretty rock. Just a nice, shiny piece of jewelry. But what we actually have here is a stone that perfectly encapsulates this massive convergence of ancient human history, deep earth volcanic mechanics, mind-bending quantum physics, and get this, a modern-day international detective story involving massive million-dollar counterfeiting operations.
It completely forces you to look at a simple gemstone in an entirely new light. I mean, you aren't just staring at a faceted crystal anymore.
Yeah.
You're looking at a captured moment of cataclysmic geologic violence. Like the very same optical principles that give this stone its color are currently driving cutting-edge metamaterials research in labs right now.
Which is insane to think about.
It is. It's a natural impossibility that somehow actually happened.
I am so ready to unpack this. Just the idea that to fully appreciate a piece of jewelry, we have to understand nanotechnology and the plumbing of a supervolcano. That is exactly my kind of topic.
It's the best kind of science story.
Exactly. So our goal today is to map out exactly how a highly specific set of cataclysmic events millions of years ago created this unique gem. We're going to explore why cutting it is basically considered the ultimate test of sanity for lapidary artists.
That'll break your heart, yeah.
And we'll break down step by step how forensic gemologists finally figured out how to spot the fakes that almost destroyed the whole global market.
For anyone listening, this story serves as a masterclass in how nature sometimes requires an impossibly lucky sequence of events to produce something beautiful.
Just a total fluke.
Completely. If any single variable in this millions of years long equation had been slightly off, if the magma cooled a century too fast or erupted a few miles west of Oregon Sunstone, just wouldn't exist.
Wow. Okay, so to understand the true value of the stone, I think we really need to start with the landscape that holds it.
That's a good place to start, yeah.
Because long before it was being graded in sterile labs or, faceted for high-end boutique jewelry, it was just being gathered right off the surface of the high desert by the northern Paiute and other regional indigenous peoples.
And the archaeological evidence for this is incredibly rich. We actually find these stones traded along extensive tribal routes stretching all throughout the American West.
But they weren't mining them like we think of mining today, right?
No, not at all. Not in the modern industrialized sense. They were collecting these glittering, weathered crystals that had essentially been pushed out of the earth by natural weathering and frost heave.
So just scattered across the dirt.
Exactly, left scattered across this desolate landscape. And they selected them for personal adornment, absolutely, but also for ceremonial applications and profound spiritual significance.
There's actually a specific northern Paiute legend in our sources that totally recontextualized the stone for me.
Oh, the battle legend.
Yeah, it describes this ancient epic battle near the Ochoko Mountains. And according to the lore, a valiant warrior was pierced by an arrow during the conflict, and his blood spilled out onto the sunstones on the ground.
Right.
And the legend says his spirit permanently colored the crystals this powerful sacred red, instilling them with mystical properties.
I love that. And that narrative carries so much cultural weight because it directly connects the intense, vivid red color of the finest sunstones, which, chemically speaking, is exceptionally rare to begin with, to life force and ultimate sacrifice.
It's so visceral.
It is. The human relationship with this stone has always been intimately tied to the extreme environment it comes from. The high desert of southeastern Oregon, specifically areas like the Rabbit Basin.
Yeah.
It is a harsh, unforgiving place. is really not an environment that welcomes human presence.
And it's so ironic that the landscape actively resists human intervention, because that exact harshness is what defeated one of the biggest commercial jewelry giants in the world.
Oh, the Tiffany story. This is amazing.
It's so funny to me. If we jump to the late 19th and early 20th centuries, European American prospectors and ranchers start noticing these bright, metallic, flashing crystals just sitting out there.
Right, just glittering in the alkali dust.
Yeah. And word eventually reaches the East Coast. And the brilliance of these stones actually attracts the attention of Tiffany and Company in New York.
Which was a big deal at that specific time in history. Tiffany was aggressively seeking unique American mined gemstones to market.
Right, they wanted a domestic luxury brand.
Exactly. They didn't want to rely entirely on European or Asian imports. So they actually went into the Oregon desert, purchased mining claims, and attempted to market these beautifully colored stones under the trade name Plush Diamonds.
Named after the tiny nearby town of Plush, right?
Yep.
But the best part is they failed. They completely abandoned the effort.
They really did.
And when you dig into the historical accounts of why, it wasn't because the stones weren't beautiful enough. It was purely because of the sheer logistical nightmare of the location.
It's brutal out there.
We are talking about extreme seasonal temperatures, like blistering triple-digit heat in the summer and freezing sub-zero conditions in the winter.
Plus an almost total lack of water.
Right, which is a massive problem if you want to run a mining operation. And virtually zero infrastructure or roads to transport the rough material out.
The environment literally starved them out. Tiffany had the capital, they had the marketing power, but it simply couldn't overcome the geography.
It's like a modern tech company realizing they can't just build a factory on Mars. Nature always has the final say.
That is a perfect analogy. You'd have to haul water in on horse-drawn wagons over miles of punishing alkali flats just to keep the workers alive, let alone run any kind of processing equipment.
So wild.
The historical value of the stone is inextricably linked to this extreme difficulty of obtaining it.
I just love that nature vetoed Tiffany and Company. So it wasn't until the 1970s and 80s, driven by these really dedicated, stubborn, independent rockhounds, that the modern revival began.
Right, the small-scale miners.
Yeah. Especially with the discovery of the Ponderosa deposit around 1980, that brought these massive, high-quality, intensely colored roughs to the global market.
Which is what really elevated the stone. The Oregon Legislative Assembly even designated it the official state gemstone in 1987.
But here's the question I kept asking while reading the sources. Why were these glowing red and green crystals just lying around in the dirt waiting to be found in the first place?
Well, to answer that, we have to rewind the clock roughly 15 to 17 million years.
Just a little bit of time travel.
Just a bit. We are diving deep into the Miocene Epoch. The formation of Oregon Sunstone is tied directly to one of the most significant and violent volcanic events in Earth's history.
The Columbia River basalt.
Exactly, the emplacement of those basalts.
When I read the volcanology sources on this, it completely changed my mental image because, when most of us hear a volcanic event, we picture a cone-shaped mountain blowing its top, like Mount St. Helens.
Sure.
But these were flood basalts.
That distinction is so vital. Forget the cone-shaped mountains. Imagine immense fissures, literally miles long, tearing open in the Earth's crust and flooding the Pacific Northwest with oceans of liquid rock.
Oceans of it.
Yeah. These lava flows were so massive they traveled for hundreds of miles, burying the landscape under thousands of feet of basalt. And the magma source driving this entire cataclysm.
Yeah.
It's the exact same deep-seated mantle plume, a colossal upwelling of superheated rock that currently sits beneath Yellowstone National Park today.
Okay, wait, let me push back on this geology for a second.
Sure, go ahead.
If the magma that created these specific Oregon sunstones came from the Yellowstone mantle plume, shouldn't we be finding these glowing sunstones all over Wyoming? Why is it only in this one specific tiny pocket of the Oregon desert?
That is the exact question geologists asked, and it gets right to the heart of why this gem is phenomenally rare.
So what's the answer?
Well, as the North American tectonic plate slowly moved over that stationary mantle plume over millions of years, it left a massive trail of volcanic destruction. But having the right magma is only the first step. According to volcanologist Dr. Emily Cahoon, who has extensively researched the geochemistry here, the sunstones are specifically hosted in two very distinct subunits of the Columbia River basalts.
The Picture Gorge basalt and the Steens Mountain flows, right?
You got it.
So what makes those two specific lava flows different from all the rest of the supervolcano's output?
It comes down to an incredibly improbable sequence of thermodynamic events that occurred long before the lava ever breached the surface. The sunstone crystals didn't form during the eruption itself.
Oh, they didn't.
No. If they had, they would just be microscopic flecks of standard minerals. Instead, these giant plagioclase feldspar crystals, some of which are massive, like up to 10 centimeters long, grew very, very slowly in deep crustal magma chambers.
Oh, so they were miles underground.
Deep in these sills, exactly.
Basically sitting in a giant geological slow cooker.
A slow cooker is the perfect way to look at it. The magma sat in those deep chambers, cooling at an agonizingly slow rate over vast stretches of time. And this stable, highly pressurized environment is what allowed the feldspar crystals to grow to such immense sizes. Crucially, because the cooling was so slow and stable, they grew remarkably homogeneously.
Meaning they were even all the way through.
Yes, and as they formed their atomic lattice, they incorporated a significant amount of trace copper from the surrounding magma directly into their structure.
Okay, so we have these massive copper-rich crystals baking deep underground. But, I mean, if they just stayed down there and the magma chamber cooled completely, they'd be locked forever inside solid rock miles beneath our feet. We'd never see them.
Precisely. And conversely, if the magma had begun to rise to the surface too slowly, the gradual drop in pressure and temperature would have caused a chemical disequilibrium.
Oh, meaning what?
Those beautiful massive crystals would have resorbed, meaning they would have literally melted back down into the surrounding liquid magma.
Oh, wow. So they would have been completely destroyed before they ever saw the sun.
Completely destroyed.
So they survived because the eruption was fast. I was reading Dr. Cahoon's paper, and the detail that blew my mind was the discovery of microscopic inclusions of a specific high-temperature pyroxene mineral locked inside the sunstones.
Yes. That pyroxene is the geological smoking gun here. High-temperature pyroxene can only form at extreme depths under immense heat and pressure.
Right.
So the fact that it is preserved, pristine, inside the sunstone means the crystal didn't have time to adapt to lower pressures.
Right.
After this long, slow period of deep growth, the magma chamber must have experienced a violent, rapid ascent to the surface.
It was essentially put on a geological express elevator.
An express elevator moving fast enough that the crystals didn't have time to melt. They were violently expelled in these highly porphyritic basalt flows, meaning lava thick with large crystals.
Okay.
Trapped in the cooling rock and then left on the surface of the earth. Over millions of years, the surrounding black basalt weathered away into desert dirt, leaving the incredibly durable sunstone crystals sitting right on top of the soil.
It is a totally unrepeatable accident. Like, you need the Yellowstone plume for the copper, you need a deep crustal holding tank for the slow cooker phase, and then you need an express ticket eruption to blast them out.
Right.
If any one of those things doesn't happen, the desert is just empty.
And that precise cooling process, both in the deep chamber and immediately after the eruption, leads us directly to the most visually stunning and scientifically complex aspect of the stone, the color.
Let's talk about the color, because this is where the geology basically turns into quantum physics.
It really does. Because the copper inside these crystals didn't just stay evenly dissolved like, salt in a glass of water. As the crystal finally cooled, the copper was subjected to a process called exsolution.
I want to dive deep into this, because most sunstones in the world, the ones you see in standard jewelry stores from India or Tanzania, they get their sparkle from inclusions of a completely different mineral.
Right. Usually iron-based, yeah, like hematite or goethite.
But Oregon Sunstone is globally unique because its optical effects are caused entirely by native copper, just pure elemental copper suspended inside the crystal structure.
And the way that copper physically manifests within the crystal lattice dictates exactly what you see. It actually produces two completely different optical phenomena based entirely on scale.
Scale of the copper.
Right. The first phenomenon is what gemologists formally call eventurescence, though anyone in the trade almost universally calls it Schiller.
Schiller. I read it comes from an old German word meaning to wink or blink or play with light.
Which is the perfect description. Schiller is caused by macroscale inclusions of copper. So during that exsolution process, as the crystal cooled, atoms of copper were forced out of the feldspar lattice and began to clump together. They formed relatively large, flat, platy crystals of pure metallic copper. Chemists refer to this as Kuno, meaning zero-valent, elemental copper.
But they don't just form random clumps, right? The host feldspar crystal has a highly specific internal architecture, and it forces these copper platelets to align themselves perfectly along the internal cleavage planes of the crystal.
Exactly. So instead of a chaotic jumble of copper flakes, you have millions of flat microscopic mirrors, all oriented in the exact same direction, suspended in a transparent medium.
So when you turn the stone and the light hits that specific angle, all those millions of mirrors reflect the light back at your eye simultaneously.
Creating this intense, blinding, coppery flash. That's Schiller.
Wow.
From a physics standpoint, it's a beautiful optical suspension phenomenon, but it's fundamentally based on classical reflection. The light bounces off a flat surface.
Right, making it sparkle.
But the second phenomenon, the transparent body color of the stone itself, the vibrant reds, the rare greens, the teal blues, that is what elevates Oregon Sunstone into a marvel of quantum physics.
See, this is where I had to read the sources 3 times just to wrap my head around it.
It's complex.
Normally, when we think about how a gemstone gets its color, we think about chemical impurities absorbing light. Like iron makes an amethyst purple. Chromium makes a ruby red.
Classical crystal field theory, yeah.
Right. But the research from the Gemological Institute of America, the GIA, explicitly states that classical crystal field theory cannot explain the transparent colors in Oregon Sunstone. The copper isn't acting like a chemical dye at all.
No. If we zoom in and look at the bigger picture of what is happening atomically, we are looking at naturally occurring nanotechnology.
That's just crazy.
The transparent body colors are caused by submicroscopic metallic copper nanoparticles dispersed as a colloid within the feldspar. These particles are so incredibly small that they actually alter the fundamental way electromagnetic radiation light behaves when it interacts with them.
Okay, when we say small, we need to give some context here. How small are these copper clusters?
We are measuring them in nanometers. A nanometer is 1/1000th of a meter.
1/100000th.
Yeah. A sheet of paper is about 100,000 nanometers thick. We are talking about copper particles that are fractions of a fraction of that size.
Unbelievable.
And the mind-blowing part is that the physical size of the particle strictly dictates the color your eye perceives. When the exsolved metallic copper nanoparticles are extremely small, specifically under 80 nanometers in diameter, they trigger a phenomenon called surface plasmon resonance.
Okay, I read up on surface plasmon resonance, and I want to try and translate this into everyday terms for a second.
Go for it.
It basically means that when a light wave hits this tiny copper nanoparticle, it interacts with the cloud of free electrons floating on the surface of the copper. And because the particle is under 80 nanometers, that electron cloud resonates at a specific frequency that completely absorbs blue and green light wavelengths.
That is a phenomenal way to explain it. It acts exactly like a highly tuned optical filter. The particle absorbs all the energy of the blue and green light, effectively deleting it from the spectrum you see, and it only allows the red light waves to pass through.
Creating that intense red.
Exactly. A highly saturated, spinel red body color.
I actually saw one of the sources compare it to ancient glassmaking.
Yes, it's the exact same physical mechanism that medieval glassmakers accidentally stumbled upon to create ruby red stained glass windows. They called it copper ruby glass.
Right, they were grinding up copper and baking it into the glass centuries before anyone knew what a nanoparticle was.
Or what surface plasmon resonance meant.
So it's literally like having a...
Yeah, and due to their specific size, they exhibit their absolute strongest extinction power, their scattering ability in the red and orange wavelengths.
So if a light beam hits a 100 nanometer copper particle, it grabs the red and orange light and violently scatters it outward, away from your eye.
Exactly. The red and orange are scattered away, which means the only wavelengths left to pass directly through the crystal and reach your eye are the greens and the blues.
That is wild. So the exact same material, pure elemental copper, makes the stone look vibrant red if the particles are 80 nanometers, and stunningly green if they are just 20 nanometers larger.
Just a tiny shift in size.
And because these nanoparticles are so incredibly efficient at manipulating light waves, you only need a microscopic amount of copper to dye the whole stone. The GIA noted that just 20 parts per million of metallic copper is enough to produce a deeply saturated color.
Yep, and if there's too much copper, the resonance is so strong the stone just goes opaque and turns black.
Which perfectly explains one of the most highly prized variations, the watermelon effect.
Oh, watermelon sunstone. Yeah, this dependency on particle size explains it perfectly.
These are stones that, when sliced open, reveal a vivid red core completely surrounded by a bright green rim.
Right.
Which seems completely counterintuitive because if you look at the chemical analysis, the red core of a watermelon sunstone actually has a much higher concentration of copper than the green rim. If there's more copper, why doesn't it just turn darker red? Why does it transition to green?
To understand that, you have to read the stone like a map of its own thermal history.
Mm.
It comes back to how the stone cooled over millions of years and the process of chemical diffusion.
Okay.
During that slow geological cooling period inside the deep magma chamber, the copy inside the crystal began to diffuse, migrating outward from the center.
Because nature hates a concentration gradient and wants to spread things out.
Precisely. The core had the highest initial concentration of copper, and, critically, it stayed hotter for a longer period of time than the outside of the crystal.
Makes sense.
This heat allowed the copper particles in the core to grow. Some grew large enough to become the massive macro-scale flakes that caused the winking Schiller effect. But this process also left behind a massive population of newly nucleated, very tiny nanoparticles, the ones under 80 nanometers.
The red filter ones.
Exactly. Those tiny particles in the center give the core its deep red color.
And as you move out toward the outer edges, the rim of the crystal.
As you move toward the rim, the overall concentration of copper drops significantly, and the cooling timeline was slightly different. The copper particles there had enough heat to grow past the 80 nanometer mark, but the crystal cooled before they could grow into massive Schiller flakes.
They got stuck.
They got stuck at that intermediate 100 nanometer size.
So the rim gets stuck in the scattering phase. It scatters the red and transmits the green.
Exactly.
Yeah.
The dramatic color zoning you see in a watermelon sunstone is actually a direct visual map of the crystal's thermal history and its internal copper diffusion gradients locked in deep time.
You are holding a literal temperature map of a Miocene magma chamber. It's breathtaking. But we haven't even touched on the most confusing visual effect yet.
Pleochroism.
Yes. Specifically the dichroic and trichroic stones. I was looking at videos of faceted sunstones to prepare for this, and the visual effect is staggering. You can look at a faceted stone face on, and it is a deep, rich emerald green. But if you tilt the stone just a few degrees in your hand, it instantly flashes into a brilliant, fiery red.
And this specific behavior raised a massive red flag for physicists when they first started studying the optical properties.
Why is that?
Well, if the color is caused by nanoparticles of copper, and we assume those nanoparticles are just tiny spheres, the color absolutely should not change when you tilt the stone. A sphere is perfectly symmetrical. It looks the exact same from every possible angle. So why does the wavelength of light shift so dramatically based on the viewing angle?
Because they aren't spheres.
They aren't spheres at all. Direct observation using ultra-high-resolution transmission electron microscopy, or TEM, finally solved the mystery. When scientists looked at the crystal lattice at an atomic level, they revealed that the copper nanoparticles are actually distorted into ellipsoids.
They're stretched out.
Yeah, looking like tiny microscopic footballs.
What on earth causes solid copper to stretch like that?
In the scientific literature, they explain that this distortion is caused by the anisotropic interfacial energy of the triclinic Feldspar host crystal.
Okay, hold on. Anisotropic interfacial energy, let's translate that into English for a second. Are you basically saying the crystal structure of the host rock is asymmetrical and it's physically squeezing the copper particles as they try to form?
That is an excellent translation, yes. Because the atomic structure of the feldspar itself is asymmetrical, it exerts uneven pressure on the copper as it exsolves. The crystal architecture essentially squeezes the copper particles, forcing them to elongate and grow uniformly in one specific direction.
So you have millions of little copper footballs, and because of the crystal lattice, they are all pointing in the exact same direction inside the gem.
Precisely. And because they are elongated into football shapes, their surface plasma on resonance, their ability to filter light changes entirely depending on which axis the light hits.
Oh, I see.
If the polarization of the light aligns with the long axis of the nanoparticle, it interacts with a different length of electron cloud than if it hits the short axis. The absorption and scattering dynamics completely change based on the angle of intersection.
So if I look directly down the long axis of all those millions of little footballs, the resonance absorbs the blue and green, and I see a brilliant red gem. But if I tilt the stone and look across the short axis, the resonance shifts to scattering the red, and the gem turns bright green.
You've got it. The stone is manipulating the physical properties of light based on directional atomic geometry. it is, by definition, a natural metamaterial.
It absolutely is. And while this level of optical complexity is a marvel for quantum physicists and an absolute delight for high-end jewelry collectors, reading through the lapidary forms made one thing very clear.
Oh boy, yeah.
This stone creates an absolute hair-pulling nightmare for the artist whose job it is to turn a rough rock into a finished gem.
Taming the sunstone is widely considered one of the ultimate tests of a gem cutter's skill and patience.
Let's talk about that lapidary challenge. Because understanding this intense directional color behavior leads directly into why this is one of the most frustrating stones on Earth to put on a cutting wheel. I want you to really imagine this. You are trying to carve a block of wood, but the grain of the wood changes color depending on how you hold your chisel.
Right.
And if you tap your chisel 1 degree too steeply, the entire block shatters into 100 useless pieces. You've just lost thousands of dollars and months of work. That is the daily reality for these artists.
The difficulty begins immediately with the fundamental physical properties of the mineral itself. Oregon Sunstone is a Feldspar, which means it has a Mohs hardness of about 6.5 to 7.2.
Which is, oh, yeah, right.
It makes it resilient enough for careful daily wear in a ring or pendant, but it is noticeably softer than standard gems like quartz, topaz, or sapphire. However, hardness isn't the real enemy here. The primary villain in the cutting room is cleavage.
And because a lot of people might not know the technical geology definition of cleavage, we aren't talking about shapes. We're talking about invisible fault lines, right?
That's a great way to visualize it. Cleavage refers to the way a crystal naturally wants to break or split along very specific internal structural planes where the atomic bonds are weakest. Sunstone features perfect cleavage in 2 intersecting directions, specifically what crystallographers call the Sirgoin planes.
So it essentially has microscopic sheets running through it, like the layers of a flaky pastry.
Yes, exactly. And if the stone is subjected to mechanical shock, like the high-speed vibration of a cutting lap wheel, or the downward pressure required during polishing, it can easily split wide open right along those flat planes, ruining the gem entirely. You can have a nearly finished masterpiece, apply slightly too much pressure on the final polish, and hear a devastating click as the stone shears in half.
So how on earth do the cutters deal with that? They can't just change the atomic structure of the rock?
They have to rely on advanced geometric engineering. When a master cutter evaluates a piece of rough sunstone, they can't just start grinding. They have to study the crystal structure and mentally map out exactly where those invisible cleavage planes are oriented.
Like plotting a minefield.
Very much so. The golden rule in faceting sunstone is that the cutter must orient the facets, the flat, polished faces they're grinding into the gem, at least 7 to 10 degrees away from any cleavage plane.
Because if they cut a facet perfectly parallel to that weak structural plane, the friction of the spinning wheel will just rip the layers right off.
Exactly. On the lapidary forums we looked at, like the International Faceting Academy, cutters shared absolute horror stories about this. One veteran cutter explicitly called it the facet from hell.
Wow.
If they miscalculate and happen to be polishing too close to parallel with that cleavage plane, the microscopic friction of the polishing grit will literally grab the atomic layers and rip microscopic chunks of material right out of the perfectly flat face of the gem.
The forums call that pulling out or pitting. You think you have a mirror polish, you wipe the stone off, and the surface looks like it was hit by a microscopic shotgun blast.
And if that disaster happens, the cutter has to employ highly specialized, often excruciatingly slow techniques to fix it without making it worse. The sources mention having to physically reverse the rotational direction of the polishing lap machine.
So the friction of the wheel pushes against the grain rather than trying to peel it up like a hangnail.
Exactly. Or, if it's a particularly stubborn stone, they have to abandon standard fast-acting oxide polishes entirely. Instead, they use a specialized bat lap, a specific type of metal alloy wheel, charged with an unimaginably fine 100,000 grit diamond spray.
100,000 grit, that's basically dust.
Pretty much. And rather than letting the machine do the work, the cutter has to manually sweep the stone back and forth by hand in a very light, highly specific arc, just to coax a clean polish out of the surface without ripping the internal structure apart.
It's surgical precision on a spinning wheel.
Yeah.
And that is just the physical mechanics of not destroying the stone. Then they have to deal with the optics.
Of a color orientation.
Right. We spent all that time talking about the pleochras and the fact that the stone changes from bright green to deep red depending on the angle because of those copper footballs. The cutter has to decide before they make a single cut which color they want facing up on the top of the gem, which is called the table.
Orientation is absolutely everything in sunstone lapidary. The cutter isn't just shaping a rock, they are actively engineering a light trap. If a client wants the finished gem to present a pure, deep, emerald green color when set in a ring, the cutter has to orient the rough chunk of rock so that the final viewing angle perfectly aligns with the short axis of those microscopic copper ellipsoids. If they're off by just a few degrees, the green will look muddy, or a red flash will constantly bleed through.
It's essentially playing 3D chess with light rays, and they have to isolate that color by manipulating the angles of the bottom of the gem, the pavilion.
Right. To prevent the red from bleeding in from the sides, they often have to cut the pavilion at very steep angles, deliberately trapping certain wavelengths of light and bouncing others away.
But they are fighting against the stone's natural physics there, too, specifically the refractive index.
Yes, Oregon Sunstone has a relatively low refractive index, or RI, ranging from about 1.563 to 1.572. The RI is a measurement of how much a beam of light bends and slows down when it enters the stone. This number dictates the stone's critical angle. For sunstone, the critical angle for light reflection is 43.5 degrees.
Okay, so if you cut the bottom facets shallower than 43.5 degrees, the light doesn't bounce off the inside of the gem and return to the viewer's eye. It just shoots right out the bottom of the stone.
Gem cutters call that phenomenon windowing. It's considered a massive failure in faceting because it makes the center of the gem look completely dead and lifeless. You can literally read a newspaper through it, like looking through a flat piece of regular window glass.
So to prevent windowing and keep the gem brilliant, lapidaries are mathematically forced to cut very deep pavilions, usually utilizing steep cullet angles of 44 to 45 degrees.
They have no choice.
But let's combine all these challenges. The raw rough they get from the miners is usually highly fractured because it was crushed as the surrounding lava cooled and contracted 15 million years ago. So the cutter is handed an oddly shaped, heavily fractured shard of glass-like rock.
A total mess, basically.
Right. They are told they must cut a very deep gem to prevent windowing, while avoiding the perfect cleavage planes by exactly 10 degrees so it doesn't shatter, while simultaneously orienting the exact 3D angle of the microscopic copper nanoparticles so the top of the stone faces up purely green.
It is the ultimate intersection of high art, optical physics, and mechanical engineering. When you understand the gauntlet that rough stone has to run, it really makes you appreciate why a master-cut, 5-carat, pure, green Oregon Sunstone can fetch prices that rival high-quality diamonds.
Seriously.
The sheer amount of skill, geometry, and pure luck required to get it out of the ground onto a cutting wheel and into a piece of jewelry intact is staggering.
Which perfectly explains the next massive chapter in our story. Whenever you have a high-value, incredibly rare commodity that requires immense effort to produce, someone, somewhere, is going to try and fake it.
The Anderson controversy. This is where our geological deep dive turns into a true crime forensic investigation.
Set the stage for us here, because this wasn't just a few fake stones sold in a back alley. This was an industry-shaking scandal. What exactly happened in the early 2000s?
Well, to understand the impact, you have to look at where the Oregon miners were at the time. They had spent decades out in the blistering desert, carefully building the reputation and value of their unique gemstone. It was rare, it was authentically American mined, and it rightfully commanded a premium price, especially for the rare reds and greens.
Right.
But then, seemingly overnight, at the major Tucson gem shows, which is the epicenter of the global gem trade, the market was suddenly flooded.
Flooded with what?
Massive, unprecedented quantities of cheap, highly transparent, vivid red and green feldspar.
And it looked exactly like the absolute best museum-quality Oregon Sunstone.
Identical to the naked eye. The dealers who were bringing this new material into the country called it andesite. Mineralogically, andesite is just a slightly different compositional mix of feldspar, very close to labradorite. But the key was the story they attached to it.
What did they claim?
The dealers claimed this was a miraculous, newly discovered natural deposit from highly remote, high-altitude mines in Tibet, and later they claimed it was coming from the Democratic Republic of the Congo.
And because it was flooding the market in such massive industrial quantities, the price plummeted. It completely destabilized the market for the genuine Oregon miners.
Exactly.
Why would a jewelry manufacturer pay thousands of dollars for a rare American stone when they could buy the exact same looking material, supposedly from Tibet, for literal pennies on the dollar?
The Oregon miners were facing financial ruin. But the story just didn't make sense to the scientific community. The sudden appearance of millions of carats of flawless red feldspar from regions with no history of such deposits triggered a massive crisis and an intense investigation by the global gemological
They
community.
had to look into it.
Oh yeah, independent experts, including highly respected researchers from the GIA and other international labs, actually mounted physical expeditions to Tibet.
They went looking for the source.
They trekked high into the Tibetan mountains to try and verify these mining claims. But what they found was a ghost story. The evidence for legitimate, large-scale mining of red and green feldspar at those locations just didn't add up. There were no massive mining camps, no infrastructure to support the volume of stones flooding the market.
So if it wasn't coming out of the ground in Tibet, where was it coming from and how did it look so perfect? The forensic gemologists went back to their labs and went to work.
And what they discovered was a counterfeiting operation of staggering scientific sophistication.
Truly mind-blowing.
They found out that this expensive Tibetan andesite was actually incredibly cheap, low-value, pale yellow labradorite and andesite being strip-mined in Inner Mongolia, China.
But pale yellow rock doesn't sell.
Right. So the counterfeiters had figured out how to artificially alter the stone. They were using a process called high-temperature copper diffusion. In essence, they had successfully figured out how to replicate nature's million-year nanoparticle process inside a laboratory furnace.
This diffusion process is wild. The scientific sources detail the exact recipe these counterfeiters used, and it is hardcore chemistry.
Very hardcore.
They would take thousands of carats of cheap, colorless, or pale yellow stones, sometimes already faceted into gems, and bury them inside a crucible. They filled the crucible with a specific, highly reactive diffusing powder, which was a mixture of copper oxide and zirconia powder.
Then they put that crucible into a highly specialized tube furnace and baked it at unbelievable temperatures. We are talking up to 1170 degrees Celsius, well over 2100 degrees Fahrenheit, for anywhere from 72 to 160 continuous hours.
What exactly is happening inside that furnace at 2100 degrees? How does the color get inside the solid rock?
Well, at those extreme temperatures, the thermal energy fundamentally alters the chemistry of the powder. The copper oxide breaks down, and the copper reduces from a stable Cu2 plus ion into a highly mobile monovalent Cu plus ion. Meanwhile, the intense heat causes the silicate lattice of the solid feldspar crystal to literally expand and open up.
Like pores opening in a steam room?
Exactly. The lattice opens, and those highly mobile Cu plus ions rapidly diffuse deep into the core of the stone, physically pushing out and replacing sodium ions in the crystal structure.
And then as they pull the crucibles out of the furnace and let the stones cool down, those Q plus ions that are now trapped inside the rock steal electrons from the surrounding crystal lattice. They reduce one final time, turning into pure metallic copper Co.
And because of the thermodynamics of the cooling process, those metallic copper atoms naturally cluster together. They form the exact same submicroscopic metallic copper nanoparticles that exist in natural Oregon Sunstone.
They successfully manufactured the surface plasmon resonance filter. The counterfeiters artificially built the 80-nanometer red light filters inside a cheap yellow rock. So when you shine a light through the fake stone, it absorbs the blue and green and lets the brilliant red pass through, exactly like a 15-million-year-old natural stone.
And this exact mechanism is what made it such a diabolical, nearly perfect counterfeit. Because the coloring agent in both the fake Mongolian stones and the natural Oregon stones is physically identical. They both use metallic copper nanoparticles. Standard gemological testing completely failed.
I read that. Conventional UV-vis spectroscopy, which labs use every day to identify gems, was totally useless. The absorption peaks of the artificial nanoparticles were exactly the same as the natural ones. The machines couldn't tell them apart.
The gem trade was in an absolute panic because they had no reliable way to certify what was real. So how did the scientists finally catch them? What was the breakthrough?
This is my absolute favorite part of the entire deep dive, because while the counterfeiters were brilliant at replicating the nanotechnology of the color, they couldn't replicate the time. Deep geological time is the one single ingredient you cannot fake in a laboratory.
The forensic breakthrough came when researchers deployed highly advanced photoluminescence and excitation emission matrix spectroscopy, or EEM. Instead of just looking at what light the stone absorbs, EEM looks at how the stone reacts when stimulated by high-energy light.
Okay, so hitting it with UV.
Exactly. The scientists took the suspect stones and hit them with a very intense, highly specific wavelength of ultraviolet light, exactly 320 nanometers.
So let's break down the chemistry of time here. What happens when you hit a natural Oregon sunstone, a stone that has been sitting in a magma chamber, cooling agonizingly slowly for millions of years with that 320 nanometer UV light?
Almost nothing happens. The natural stone shows weak or completely absent fluorescence
Why is that?
because it had millions of years to cool. During that vast span of deep time, nearly every single copper ion that was originally trapped in the crystal lattice had plenty of time to fully exsolve, migrate, cluster together, and become stable, zero-valent metallic copper particles. The internal crystal lattice is essentially clean of any stray, unbonded copper ions.
But the fake stones, they were rushed. They were baked in a furnace for 72 hours, not 15 million years.
Exactly. When the scientists hit the treated Mongolian andesite with the exact same 320 nanometer UV light, the stones lit up like a neon sign. They exhibited an intense, blazing orange to red fluorescence.
The spectroscopic data showed a massive emission spike right at 394 nanometers and a secondary bump at 555 nanometers.
Those specific emission spikes are the forensic smoking gun. They are exclusively caused by high concentrations of unstable, unexsolved, monovalent copper ions, Q plus distillate.
The intermediate stage.
Right. Because the laboratory heating and cooling process was so incredibly rushed compared to a geological timeline, millions of these Q plus ions got trapped. They were frozen inside the silicate lattice mid-transition, unable to reach other copper atoms to form metallic clusters before the stone cooled and the lattice slammed shut.
It's literally like finding wet paint on a centuries-old antique masterpiece. Those glowing Q plus ions under the UV light are the wet paint of a rushed counterfeiting job.
That is a brilliant way to conceptualize it. The fluorescence was the wet paint. And once the gemologists knew exactly what anomaly to look for, they unleashed other advanced techniques to confirm the fraud. They used LAICPMS, which stands for Laser Ablation Inductively Coupled Plasma Mass Spectrometry.
That's a mouthful.
It is. This machine essentially shoots a microscopic laser at the stone, vaporizes a tiny invisible speck of it, and analyzes the exact elemental makeup to map the total copper concentration.
And what the LAICPMS revealed was that the artificial diffusion process is actually really inefficient. To get the same deep, vibrant red color as a natural stone, the lab-treated stones had to be absolutely stuffed with total copper. They were finding concentrations of over 1,000 parts per million in the fakes, whereas the natural Oregon stones only needed an elegant 20 to 180 parts per million to achieve the same color.
They also utilized argon isotope testing, which is a fascinating application of radiometric dating. Trace amounts of potassium inside the feldspar naturally decay into radioactive argon gas over millions of years at a strictly known rate. It's an internal geological clock.
Right.
But when you subject a stone to 1170 degrees Celsius in a lab furnace for days on end...
all that trapped argon gas boils right out of the stone.
Exactly. The intense, artificial heat completely resets the radioactive clock back to zero. So instead of testing at 15 million years old, like a true Miocene basalt inclusion should, the argon clock on the counterfeit stones tested as if they were born yesterday.
So through this massive collaborative effort combining photoluminescence to reveal the trapped wet paint Ia plus ions, laser ablation showing unnaturally stuffed copper levels, and argon testing proving they had been recently superheated, the gemological community finally had definitive, unarguable proof that Tibetan andesite was officially exposed to the world as a massive artificially treated counterfeit.
It was a massive victory for science, but the damage to the market was severe. Which brings us to the aftermath and how the Oregon Sunstone community operates in the modern marketplace. Because a scandal of that magnitude, flooding the market with fakes, could have permanently destroyed consumer trust in the stone.
How does a small group of local miners in the remote Oregon desert actually protect a global market from well-funded international counterfeiting operations?
Well, they realized that their greatest asset wasn't just the sheer beauty or the quantum physics of the stone. Their greatest asset was the undeniable transparency of its origin. To combat the influx of treated material, the local miners banded together and formed a coalition, the Oregon Sunstone Miners Association, or OSMA.
And if you look at the mining landscape in Oregon today, it is a truly fascinating mix of public access and regulated industry. On one hand, you have the Bureau of Land Management public collection area in the Rabbit Basin. This is a massive tract of land where anyone, a family on vacation, a hobbyist rockhound can drive out there, pitch a tent in the sagebrush, and dig for sunstones entirely for free as long as they only use hand tools like shovels and picks.
It's an incredible recreational and educational resource.
But on the other hand, supplying the high-end commercial market, you have the private, mechanized claims surrounding the public area and further up in Horny County. Legendary mines like the Ponderosa, the Dust Devil, and the Sunstone Boot Mine.
And these aren't massive strip mining conglomerates. These are small-scale, fiercely independent, U.S.-regulated mining operations. They operate under strict federal and state permits, and they are legally required to perform extensive environmental restoration when the mining is completed.
And it is these professional operations that make up OSMA. By organizing into a formal association, they were able to establish and enforce strict ethical and transparency standards.
They created an unbreakable, documented chain of custody from the dirt to the jeweler's bench. If a designer or a consumer buys a stone from an OSMA member, they receive a guarantee that the stone is 100% natural, entirely untreated, and ethically mined right here in the USA.
And they took it a step further to protect their brand. In 2015, after years of effort, they successfully registered Oregon Sunstone as a legally protected trademark. By aggressively educating buyers, jewelers, and auction houses about the undesign fraud, and relying on the advanced lab science we just discussed to verify authenticity, they didn't just survive the scandal.
They thrived, really.
They successfully carved out a highly premium, protected niche in the global jewelry market.
They turned the scandal into their greatest selling point. In a broader gemstone industry that is often plagued by totally opaque supply chains, undisclosed treatments, and ethical concerns, Oregon Sunstone offers a transparent, verifiable alternative.
It's a great comeback story.
And the economics of it work. The value curve for genuine Oregon Sunstone is steeply exponential. A high-quality, masterfully faceted red or green sunstone over 5 carats can command incredible prices. Not just because it's pretty, but because the market now understands the absolute rarity of finding a large, flawless, weathered megacryst that survived tectonic transport, violent eruption, and extraction without fracturing.
By firmly connecting the ethical governance of the stone to its perceived scientific value, the local community essentially saved their own industry. They ensured that Oregon Sunstone remains recognized not just as a piece of jewelry, but as an unrepeatable accident of deep time.
So as we wrap up this incredibly layered deep dive, I think we need to just take a step back and summarize the sheer, staggering improbability of what we've been talking about today.
Yeah.
Oregon Sunstone is quite literally a masterpiece of Earth's history.
It truly is. We are talking about a gemstone born in a supervolcanic inferno, slowly gestated in the deep pressures of the Earth's crust, colored by naturally occurring quantum-level metallic nanotechnology, revered by ancient indigenous cultures for its spiritual connection to life and blood, and finally protected by modern forensic spectroscopy and ethical independent miners.
For me, the most striking takeaway from all these sources is the realization that the reason this one specific harsh corner of the Oregon Desert produces an irreplaceable gem comes down to a geological recipe that is almost magmatically impossible to replicate anywhere else in the universe.
The odds are just astronomical.
The Yellowstone mantle plume provided the highly specific copper-rich chemistry of the magma. The crust provided the exact pressure and temperature chamber required for slow growth and nanoparticle formation. And a sudden, violent eruption delivered them to the surface just moments before they could melt away back into the Earth.
It is the definition of an unrepeatable accident. When you hold one of these faceted stones in your hand and you watch it flash from green to red, you aren't just looking at a rock. You are holding a frozen, interactive snapshot of Miocene volcanic plumbing.
And I think that leads to a rather profound and slightly mysterious thought to end on. Consider the sheer scale of the geology involved here. The Columbia River flood basalts are some of the largest, most expansive lava flows in the entire history of our planet. They cover immense, unimaginably huge swaths of Washington, Oregon, and Idaho, millions of acres of volcanic rock.
Wow.
And yet, human beings have only explored a tiny, microscopic fraction of what lies beneath the surface.
Which really makes you wonder, if a random, highly improbable collision of copper and magma could create a glowing, color-shifting gem governed by quantum nanotechnology in this one specific tiny area of the high desert, what other completely undiscovered mind-bending phenomena are locked away inside the millions of tons of basalt right beneath our feet, just waiting for the Earth to weather away and reveal them to you?
It's a humbling reminder that the Earth still holds profound secrets we haven't even begun to imagine hiding in plain sight.
Definitely something to think about the next time you see a shiny rock sitting in the dirt.